Hello everybody, welcome to another Mac Deep Dive video. If you've ever wondered how to actually measure the real performance of your Apple Silicon chip, this video is made for you. I'm going to walk you step by step through a simple demo that lets you measure the two things that matter most, compute throughput and memory bandwidth. We'll use just two tiny kernels, one to max out the compute units and one to saturate the memory system. And from that, we'll build a complete empirical roofline model of your machine. Everything is simple, reproducible, and you can follow along on your own Mac. Let's get started. Before we look at the actual benchmark numbers, I want to introduce a mental model that we will use to set our expectations on performance. This is the so-called Roofline Model. It tells you whether your code is limited by compute power or memory bandwidth. With just two measurements, you can see exactly where your workload sits and what's holding it back. There are two dimensions at play. On the y-axis, we have the familiar compute bandwidth in gigaflops, and on the x-axis, we have the so-called operational intensity, which is measured in flops per byte. Operational intensity is the ratio of operations per byte of DRAM traffic, and is a function of a problem's complexity and is not a property inherent to a particular CPU or GPU. There are two important lines in the Roofline model. The angled line is determined by the computer's peak memory bandwidth and the horizontal line by its peak compute bandwidth. The roofline will look different for different CPUs. For any computational problem, we can find a point on the x-axis based on its operational intensity. If we draw a vertical line from that point upwards, the actual performance of the computer will lie somewhere along that line up to the roofline. If the vertical line hits the flat part of the roof, we say that the problem is compute bound. However, if it hits the angled part of the roof, the problem is memory bound instead. In the picture, we can see two compute kernels. One with an operational intensity of 0.25 flops per byte on the left is memory bound, and the other with an intensity of 4 is compute bound. Note the ridge point, where the angled and horizontal roofs meet. The x-coordinate of the ridge point is the minimum operational intensity required to achieve peak performance. If the point is far to the right, then only kernels with very high operational intensity can achieve max performance. If it is far to the left, then most computational kernels will be able to reach peak performance. As we shall soon see, the ridge point will move significantly between Apple and AMD CPUs. To measure peak memory bandwidth, we need a kernel that is purely memory bound, and AXPY is a perfect candidate. The operation is simple, y equals alpha times x plus y. For each element, we perform just one multiply and one add, so that's two floating point operations. But look at the memory traffic. For every element, we read x, read y, and then write back to y. That's 3 memory accesses, or more precisely 2 reads and 1 write. Now, since we're using float32, each element is 4 bytes, so in total we move 12 bytes per element. Therefore we have 2 flops, 12 bytes of memory traffic, which gives us an arithmetic intensity of just 1/6 of a flop per byte. And that's the key point. This is an extremely low compute-to-memory ratio, which means performance is completely dominated by how fast we can move data, not how fast we can compute. In other words, AXPY forces the system to operate at the memory bandwidth limit, making it an ideal kernel for measuring peak bandwidth. To measure peak compute throughput, we need a kernel that is the exact opposite of AXPY, one that is compute bound, not memory bound. That's why we choose matrix multiplication. Here, we multiply two matrices, A and B, to produce matrix C. Each element of C is computed as a dot product between a row of A and a column of B. The process is repeated for each row of A and each column of B. Now let's look at the numbers. For an n by n matrix multiply, we perform n squared dot products, and each dot product requires n multiply add operations. That gives us a total of 2n cubed floating point operations, but the memory traffic is much smaller in comparison. We read matrices A and B once and write matrix C once. That's about 3n squared memory accesses, specifically 2n squared reads and n squared writes. So, as n grows, the ratio of computation to memory access scales as O of n. That means each byte loaded from memory is reused many times in computation. And that's the key. Unlike AXPY, which is dominated by memory movement, matrix multiplication keeps the compute units busy and minimizes the pressure on memory. So performance is no longer limited by bandwidth. It's limited by how fast the processor can execute floating point operations. And that's exactly what we want, a kernel that pushes the system to its peak compute throughput. To reproduce this demo, you will need to download Julia, and you will need to install Mactop. The links are provided in the video description. Let me show you the setup. In the top left, I'm running the experiments in Julia. This is where we launch our workload kernels, switching between CPU, GPU, and AMX, while keeping everything else as consistent as possible. At the bottom left, I'm using Mactop. This gives us Apple's internal energy model, CPU power, GPU power, DRAM power, and total system DC power. It's a convenient way to get a first-order breakdown of where the energy is going. But we don't want to take that at face value, so in the middle I have a wall plug power meter. This measures the actual power drawn from the wall, independent of any model. It's our ground truth, and it lets us sanity check what Mactop is reporting. And on the right, TG Pro shows temperatures and fan speed, so we can verify that the system is thermally stable and not throttling during the runs. In this Julia session, we're building up the two key measurements behind the Roofline model, memory bandwidth and compute throughput, starting with the CPU. We begin by loading two packages. Linear algebra gives us access to optimized numerical routines like BLAS, basic linear algebra subprograms. Benchmark tools provides accurate and repeatable timing, which is essential when measuring performance at this level. Next, we define our problem size n equal to the power of 30 and allocate two very large float 32 vectors x and y. At this size, the data sits entirely in main memory, so we will be measuring true DRAM bandwidth, not cache. The first benchmark is a simple element-wise addition. We compute the sum of vectors x and y and store the result in y. Importantly, in Julia, this compute kernel runs single-threaded by default, so it effectively measures single-core memory bandwidth. Observe the memory bandwidth shown by Mactop. This is not actual measured bandwidth, but inferred through a model based on DRAM energy. Instead, we will use our observed runtime and convert it into bandwidth using the formula length of the vector y times 4 bytes times 3. Here's why. Each element is a float 32, so that's 4 bytes. For every operation, we read x, read y, and write back to y. That's 3 memory operations per element. Multiply that by the vector length, divide by time, and you get total bytes per second. Using the fastest observed time, this gives us about 162 gigabytes per second, which is the single-core bandwidth. Next, we switch to the level 1 BLAS routine AXPY. This performs the same mathematical operation, y equal a times x plus y, but now through a BLAS kernel. And this is key. BLAS is multi-threaded, so with a single line of code, we now engage all CPU cores. You can see in Mactop that all the P cores are now loaded and that the observed DRAM bandwidth is significantly higher now. Applying the same bandwidth formula gives us roughly 360 gigabytes per second. That's our multi-core peak memory bandwidth obtained with a very simple kernel. Now we move to the GPU. We load Metal and transfer the vectors into Metal arrays. Metal is Apple's low-level GPU programming framework. Think of it as the bridge between your code and the GPU. When you write code in Julia and use Metal, you're telling the system, run this computation directly on the GPU instead of the CPU. Under the hood, Metal handles things like sending data to GPU memory, launching parallel kernels across thousands of threads, and synchronizing execution so you can measure performance correctly. The key idea is that the GPU is designed for massive parallelism, so operations like vector updates or matrix multiplication can run much faster than they would on the CPU. In this demo, when we switch from regular arrays to Metal array, we're not just changing data types, we're moving the entire computation onto the GPU using Metal. We benchmark AXPY again, this time wrapped in metal sync to ensure accurate timing. Observe again the memory bandwidth indicated by MACtop. Applying the same formula gives us about 505 GB per second, representing the GPU's memory bandwidth. Now we switch to compute throughput, using matrix multiplication. We reduce the problem size to n equals 16,384 and allocate 3 large matrices A, B, and C. These are dense float 32 matrices, large enough to keep the compute units fully occupied. We benchmark Malbang CAB, which performs an in-place matrix multiplication. This operation has very high arithmetic intensity, meaning each byte loaded from memory is reused many times. So it's ideal for measuring peak compute performance, not bandwidth. To convert the measured runtime into flops, we use the formula 2 times n to the power of 3, which is the total number of floating point operations in a matrix multiply. Dividing by time gives us about 1.28 teraflops on the CPU. To run on the GPU, we convert the matrices again into metal array. And we run the same Malbang routine, but this time it will dispatch the computation to the GPU. Using the same flop calculation, we determine the GPU compute throughput at about 13 teraflops. So in this session, every step is deliberate. A simple single-threaded kernel for baseline bandwidth, a blast kernel for multi-core scaling, and matrix multiplication to reveal the compute ceiling on both CPU and GPU. What you're looking at here is the empirical Roofline model for the M4 Max CPU, built entirely from our own measurements. On the x-axis, we have arithmetic intensity. That's how much compute work you do per byte of memory accessed. On the y-axis, we have compute performance in gigaflops. This diagonal line represents the memory bandwidth limit. In this region, performance scales linearly with arithmetic intensity, because the CPU is starved by memory. Then, at this point here, around 3.5 flops per byte, we hit the knee of the curve. Beyond this point, the system becomes compute bound. The flat line at the top shows the maximum compute throughput, which we measured at about 1280 gigaflops. So below the knee, memory is the bottleneck. Above the knee, compute is the bottleneck. And this is the key idea behind the Roofline model. It tells you exactly what's limiting your performance, depending on your workload. This table highlights how memory bandwidth scales across Apple Silicon generations, and the jump from M1 Max to the M4 Max is especially striking. Starting with the M1 Max, we see about 102 GB per second on a single core, scaling up to 224 GB per second across 8 cores. Now compare that to the M4 Max. A single core already reaches 162 GB per second, which is roughly a 60% increase. This carries over to multi-core scaling. With 12 cores, the M4 Max hits 360 GB per second. That's again a 60% uplift over the M1 Max. This isn't just faster memory, it's a combination of higher memory speeds, improved memory controllers, and higher CPU frequency. And when you compare that to something like the Ryzen 9900X, which sits around 60 GB per second and doesn't scale with threads, the architectural difference becomes very clear. This diagram shows the memory communication path used by Zen CCDs. The slide is from Zen 4, but the Ryzen 9900X on Zen 5 uses the same fundamental structure. And the key to understanding its memory behavior is in these 2 yellow highlighted links. Let's start with the first one, between the L3 cache and the Infinity Fabric. This is the path every cache miss takes when data leaves the core complex, and importantly, this link is asymmetric. One side can move 32 bytes per cycle while the other is limited to 16 bytes per cycle. So even at this stage, the data flow is already constrained before it even reaches the rest of the system. Now follow the second highlighted path, from the Infinity Fabric to the Unified Memory Controller or UMC. This is the critical bottleneck. That link is limited to 32 bytes per cycle, and with a fabric clock of about 2 GHz, that translates to roughly 64 GB per second of total bandwidth. Now compare that to the memory itself. In this system, we're using DDR5 5600 in dual channel, which has a theoretical bandwidth of about 90 GB per second. So the DRAM is actually capable of more bandwidth than the fabric can deliver. And here's where the architecture really matters. The Ryzen 9900X has two CCDs, but both of them connect through the Infinity Fabric to a single I/O die, which contains just one unified memory controller. So both CCDs, all of their cores, all of their memory traffic have to pass through the same 64 GB per second link into a single memory subsystem. That means the bottleneck isn't in DRAM, it's in the on-chip data path. Even if the cores can generate more demand, and even if the memory is fast enough, the system simply cannot move data through the fabric any faster. And that's why these CCDs are effectively memory starved. Not because the memory is slow, but because the internal pathways feeding it can't keep up with the combined demand of both chiplets. From our measurements, we found that a single Apple Silicon core can reach memory bandwidth numbers that are several times higher than what we see on a Zen 5 core. That's a huge architectural difference, and it's not just about faster memory. In the next video, we'll take a closer look at why that happens, from the memory system to the cache hierarchy to the way data actually moves through the chip. Because once you understand that, you start to see why these performance gaps exist. Everything we did here is simple, reproducible, and you can run it on your own system, whether it's Apple Silicon, Intel, AMD, or something else entirely. The code for the CPU will be the same, only the GPU part will differ. I'd love to see what you get. If you try this out, come back and share your results. Include your system specs, your single core and multi-core CPU bandwidth, your GPU bandwidth, and your CPU and GPU compute throughput. The more data we collect, the better we can understand how these architectures really compare in the real world. So give it a try and let's build this dataset together.